Hello everyone, we are team 142 and we are presenting our project Mini-DFS or Mini Distributed File System. Introduction slide. Mini-DFS is a lightweight and educational model designed to clearly demonstrate how real-world distributed file systems work. The system is built to show key concepts such as chunking, replication, metadata management, heartbeat-based node monitoring, failure detection, and automatic re-replication. All of this highlighted in the project description and introduction. It also includes modern features like blockchain-based metadata ledger to ensure transparency and immutability, and a plugin-driven architecture that supports carbon-aware decisions, chaos testing, bio-inspired replication, and delay-tolerant networking. Next, problem identification. Next slide. Problem identification. The problem identification described in this project emphasizes the traditional centralized storage suffers from single point of failure, limited scalability, and low fault tolerance. The files also clearly point out that existing distributed file systems like HDFS, Ceph, and GFS are too complex, heavyweight, and difficult for students to deploy or understand. And they provide very limited visibility into replication decisions, node failures, or internal metadata processing. There's also a gap where existing systems do not offer blockchain-based transparency and do not support plugin-based adaptive replication strategies, as mentioned in our literature review and research gap sections. Mini-DFS was specifically created to address the limitations by providing a simple modular, transparent, and student-friendly DFS. This includes chunk replacement, node health re-replication, and metadata history. Next.
Coming to the literature review, Google File System. A Google File System introduces a chunk-based storage with a single master managing all metadata. It was mainly designed for Google's large-scale workloads. This architecture is powerful but too complex for small educational system. Coming to the HDFS, Hadoop File Distributed System is an open source version inspired from GFS and widely used in big data platforms. It stores large files across clusters using NameNode and DataNodes. Although efficient for industry use, it requires heavy setup and resources. This makes it difficult for beginners to understand or deploy on small system. Next, IPFS. IPFS uses content addressing where data is justified by its hash instead of its physical appearance. It can be challenging for students to grasp without strong networking knowledge. Other DFS research. Many research works focus on improving replication, failure detection, and metadata consistency. These advanced techniques enhance performance but increase system complexity. As a result, they are not always suitable for teaching basic DFS concepts. Gap identified. Gap identified. Existing systems are complex and heavy for small scale learning environments. Students struggle to understand internal mechanism like failure detection. There is a need for simpler model that shows how distributed storage works. A lightweight DFS can help learners clearly observe failures, replication, and recovery. Next slide, please. Coming to the objectives, here the first objective to design and build lightweight distributed file system suitable for learning and small projects. Next, to create data nodes that store file chunks and send heartbeats to show they are active or not. To support basic operations like file upload, download, list, and delete. To develop a master node that manages a metadata and controls chunks replication. To ensure automatic recovery by re-replication data when a node fails. To add plugin based intelligent replication so different strategies can be tested easily. To integrate a blockchain ledger to keep metadata records secure and immutable. Thank you. Next slide. Continue.
Now coming to the proposed system architecture, there are four in it: master node, and a data node, then API gateway and client. The master node manages a metadata, and it also segregates the chunk data from data nodes, and it is a main component of it also do some re-replication logic, blockchain recording, etc. And this is the main master of the our code. Then coming to the data nodes, in data nodes, data nodes are the point where the files we stored in them will be get dissolved type in chunks format. Like if we send an example text will be divided into multiple chunks and will be stored in multiple data nodes for data redundancy. And it also sends a heartbeat to the master for to check whether the data node is alive or not. And it can also perform a replication process when instructed by master. And coming to the API gateway, it converts the UI REST calls into master socket commands. Like if a client can upload or delete the data, the API key will be sent from the master node to the client. Then the operation the user the requires will happen. And coming to the client or UI, he can perform upload, download the blockchain. You can also view the blockchain ledger and node health. Next slide, please. And this is our architecture diagram. Here we can see in master node there are heartbeat monitor and metadata manager. Heartbeat monitor will manage the node health from data nodes, and metadata manager will manage the file chunks. The client uh, the client can perform operations like uploading a file, getting a file, viewing the uh, blockchain ledger, and also deleting a file. As you can see clearly below the data nodes, it stores and serves chunks, and master node it stores metadata file to chunks and monitors data node health and detects failures. Next slide, please. Here is a detailed component. First, the main component is master server. In the master server code, it handles a replica management logic and chunking logic, and it also manages the metadata JSON file, which is responsible for storing the ledgers. The action ledgers are nothing but the actions we performed, and it also records every blockchain event. And coming to the next data node logic. In data node logic, the local chunk storage code will be recorded in it, and heartbeat logic also will be recording it, like to send the ping to the master server and replication of the logic. And coming to the plugin, in plugin we have added delay-tolerant routing, chaos testing. Chaos testing is nothing but we are running our code in a stress strain environment to manage our check the efficiency of a code, and carbon aware placement and bio inspired replication. And finally, blockchain ledger. It's nothing but the storage point of our entire code. Next slide.
Methodology and workflow. File uploading into the system. User selects a file in UI where the UI sends request saying I want to upload this file. At the time, API gateway forwards the request to the master node. Master node creates an upload metadata record. Master node breaks the file into multiple smaller pieces such as chunks. Plugin selects the best data node where chunks can be stored. After the chunks are stored successfully, metadata will be updated so that the transparency is maintained in the blockchain. Next slide, please. File download workflow. User requests a file from UI where the API gateway sends the request to the master node. Master node knows the location of every chunk which is stored. So the data node sends the chunks back to the user, and user system reassembles the chunks into a full file. While the uploading or downloading a file, few failures may happen. Data node sends heartbeats of a person every second. If the data node stops responding, then the master node marks it as dead. Master node automatically duplicates the lost changes of the healthy node. So blockchain logs replicate an event into keep everything permanently. Next slide. For this, we have few special features such as metadata stored in the blockchain secures it is for securing and the maintaining transparency. Replication is for to maintain an extra copy of the data which happens in an automated and a rule based way. AI helps us to decide what data to be stored, how to optimize the chunk distribution, and how to balance the workload. System can choose data node on every consumption. Even if a node fails, data is saved because the chunks are replicated. Users users can easily understand because we use the Python language for the clear development and flexibility. Pure Python socket architecture for simplicity. Continuously chunks and nodes are there so that they can detect the failures quickly. Next slide.
Coming to tech stack, we have done our front end with React.js, Vite, Tailwind CSS, and Axios. It is easy to build a fast interactive UI for uploading. And coming to API layer, we have done with FastAPI and Pydantic. FastAPI works as a REST API gateway between UI and the master node. And for the backend, we have used Python sockets and threading. And for the storage and metadata, we had local chunk folders, a master metadata JSON file, and blockchain JSON file. And for plugins and mix tool, we have done modular Python plugin framework and also used VS Code, Git, GitHub, Postman, Swagger docs. For implementation, the first part is DataNode architecture, where the master handles metadata, chunk assignment, replication, and node. And the data node stores the chunks and send the arg bits, act as a replication commands, and the communication is fully based. And coming to file chunking and replication, files are split into fixed size chunks before storing, and the replication factor is equal to 2. So each chunk is of 2 replicas. For argbit based failure detection, every data node sends argbit messages every few seconds. And if the master stops receiving argbits, node is marked as dead. And master automatically triggers re-replication of lost chunks. And for fast API integration for UI, React frontend never talks directly to sockets. So instead, it communicates via fast API, which receives HTTP requests, converts them into sockets, and return results back to UI. And for blockchain ledger for transparency, all events like upload, delete, download, and replicate saves as a blocks. And the block contains timestamp, file or chunk details, and hash and previous hash. This provides the tamper-proof metadata history, a unique innovation in our DFS. For React-based modern UI, it allows easy for file upload and download, and it has clean separate pages for upload, download, file tables, blockchain viewer, node dashboard, and plugin control panel. And UI also clearly shows active nodes, which is marked in green color, and dead nodes, which are in red color, and blockchain data. And for plugin for intelligent application, our DFS supports multiple intelligent plugins like Carbon Aware plugin, which chooses nodes based upon low energy cost, and BioInspired plugin, which replicates chunks in diverse locations similar to biological space systems. And Chaos plugin, it simulates random node failures for testing DFS resilience. And delay-tolerant plugin, which helps unstable or disconnected networks. And next is Swagger API documentation. It is used for testing HTTP routes, and it is easy to use when we are using fast API. and it helps debugging upload and download operations directly from the browser.
As for the results and outputs, first one is upload and download. Files are uploaded through the React UI without errors. Master splits the files and assigns chunks and stores them correctly. Download reconstructs the original file perfectly from all the chunks. The second one is blockchain ledger working. Every operation such as uploading, deleting, and replicating is recorded as a new block. Each block contains its own timestamp, file chunk details, hash, and its previous hash, ensuring immutability and transparency of operations. Next slide, please. The third one is automatic failure detection. When a data node stops sending heartbeats, it is marked as dead. Master logs the event and starts recovery procedures. Dead node status is known clearly in the UI. And the fourth one is re-replication of node failure. When a node fails, the chunks, the lost chunks are automatically re-replicated to the healthy nodes, ensuring no data loss even when a node goes offline. Blockchain logs a replicate event. The fifth one is node health monitoring. UI dashboards displays active nodes are marked as green and inactive and offline nodes are red. Updates the real time based on heartbeat messages. Next one, please. The conclusion of the Mini-DFS. The Mini-DFS system performed successfully across all the tests. File uploads were processed correctly, with the master node splitting files into chunks and storing them across data nodes. Downloads accurately reconstructed the original file, proving the reliability of the chunking mechanism. The blockchain ledger recorded every operation such as upload, delete, and replicate, ensuring transparency and immutability. The system detected the node failures instantly through missing heartbeats. When a data node went offline, the master triggered automatic re-replication to healthy nodes, preventing data loss. The user interface clearly displayed the live and dead nodes status in real time. All plugins executed properly, including Carbon Aware and chaos testing. Overall, the Mini-DFS demonstrated reliable storage, strong fault tolerance, and transparent metadata tracking. Next one. As for the future scope of the Mini-DFS, AI-driven replica placement and node scoring. Second one is cloud native DFS deployment, multi-master DFS coordination, versioning and snapshot support, caching layers, edging, edge and satellite-based DFS optimization, vast browser data nodes, mobile UI for distributed monitoring. Thank you. Next.